Hello, everybody. Can everybody see me?
Yes,
Hello,
sir.
everybody. Good morning. Can everybody see me?
Yes.
Okay, wonderful. All right, thank you. Basically, what we're going to be doing today is essentially continuing where we left off, but I wanted to talk about the worksheets. Please, for those of you that are virtual, please turn them in by the end of my office hours today, which is 1:15, and I'll give you credit for doing them. But the whole purpose was to get you ready for the exam on Thursday. The exam basically for the sports people, I have 5 sports people. You'll be doing in present lecture. They'll be coming at 8 o'clock. The others who are coming in person will come at 7, and about 4 or 5 of you from the 8 o'clock. If you want to come at 7 o'clock, you can do that too. So basically, it should work out just fine regarding what's going on with that. You'll be allowed to have a 3x5 card on both sides with whatever formulas or whatever you want to do it. But the best thing to do, and the periodic table I'll provide you, the periodic table, essentially the best thing for you to do between now and thing is continue working on the problems for chapter 3. But the main, because it uses the stuff on chapter 2 that finishes up the stuff, the worksheets that I asked you to work on over the weekend is related to chapter 2, going grams to moles, and basically you just have to learn how to do it just by practicing it. So basically it will go pretty well if you just trust me and put in the work you need. Now also, because we have 4 tests, if you don't do very well on this test but do well on the rest, that's fine. That's sort of normal, okay? Because what I want you to see is what you know at the end of the semester, not worry about their struggles at the beginning, because everybody has to learn this new stuff, a new way of thinking and other things. So I do want you to keep that in mind. But the main thing I want you to understand is the nature of how these things work regarding grams to moles, or moles to grams. It's just a very simple conversion that you're being asked to do first, and then doing basic conversions like temperature and other stuff like that. And the key thing is, if you've practiced them enough, you'll be able to do those as well. So what we're going to do now is shift to the PowerPoint. Now, so I'll get that set up. First, before I go into that, are there any questions that any of you might have regarding what's going on regarding the lecture or the preparing for the exam on Thursday? Now, the other sections had the exam last week. I decided to give you an extra week just because I decided to do that, and because everything was jammed up all in 1 week last week anyway with other tests. And so basically, it was just my decision to wait a week with this. But because they're every 2 chapters, I'll be continuing with chapter 3 today, and we'll probably finish it by Thursday, and then we'll continue with chapter 4. So once we're done chapter 4, there'll be a relatively short distance between 4 and the next exam. Like, for example, if I finish on Thursday, the exam will be on Monday the next week, okay? Because I want to give you plenty of time to do that. So basically, the thing will be relatively short just because of the nature of the semester. Are there any questions regarding how that will work? Anybody? Okay.
Dr.
Yes.
So the information from chapters 3 will not be on the test.
Well, only the stuff from chapter 3 that's common to chapter 2 will. And the worksheets that I did over the weekend will be. But that sort of overlaps. It isn't very clean, the barrier. There is a clean barrier between 4 and the next chapter, whatever the next one is, because then we're going on to orbital theory and such, okay? So basically, that's how that's going to work, okay? Let's go to the next slide here first. Okay, I'm going to share the screen with you now. People with the Zoom, so hold on a minute. Okay, can everybody see the screen now with this? Can you see
Yes,
the
sir.
PowerPoint? Can you see the PowerPoint?
We can.
Okay, thank you. Trying to get this to play. Hold on 1 minute, please. I don't know what's going on with the thing. Hold on a minute. I got to get the slideshow going again. Just a sec, please. I'm trying to get this resolved here. Okay, can you see the screen now? Is everything fine with that?
Yes.
Okay, wonderful. Okay, now, one of the things that needs to be understood regarding the nature of how these things work, hold on a sec, is understanding the difference in terms. For example, there's the thing of here, which is formula mass and molecular mass. Okay, formula mass is the sum of atomic mass in an ionic compound. The molecular mass is the sum of the atomic masses in a covalent compound. In other words, one molecule. Okay, and they're bonded differently. We'll learn about the difference in bonds a little later. But the main thing to understand the distinction between formula mass and whatever is the fact when you have a salt, it's in a big network thing. So essentially, it could be it would be many atoms of one and many atoms of the other. So let me go to the next thing here, raise what's on the slide, and we'll continue with the thing to show you how this works. But basically, here, for example, sodium chloride. That is a small crystal of sodium chloride. If you notice the red things, that is the chlorine. The red things here, this is the chlorine, it's bigger, and the small one is the sodium, okay? So essentially you have the things together, but you notice there are many of them, but they have what's called a common factor. So they're divided you can divide them by the common factor, and it comes down to NaCl, which would be 1 to 1. But it doesn't matter if it's N 1,000, chlorine 1,000, or N 1,000,000 thing. It could be 1,000,000, it could be 1,000, like say, for example, sodium 1,000, chlorine 1,000. The common thing is it's 1 to 1. You just divide both sides by 1,000 and you get the whole thing. So that's what formula mass is essentially there, okay? So chlorine, the formula mass of that is 35.45 AMU. You add the two together, and that is the formula mass of this. Now, this is interchangeable with molecular weight when you convert it to grams. So how much is the mass of 1 mole of sodium chloride? What's the mass? Yeah, 58.44 grams. So the conversion is AMU goes to grams when you bring in the whole thing of the moles, okay? The AMU just has to do with the standard 1 atom of each, an average of all of them, an average, a weighted average of them. So essentially you have essentially a group of things working together there. So essentially the formula mass at AMU is equal to the molar mass in grams, okay? Same thing with the molecular mass in molecules. It's still the molar mass. Okay, so 1 formula unit AMU there, and 1 mole of sodium chloride is that. So essentially, if we have a situation where you're asked for the formula mass, how would you do this problem? And you will always have a periodic table in front of you. How will you do this problem? Let's work through it together. What do you start with? Yeah, go ahead. Go ahead. What do you start with?
Find the molar mass.
Right. So which element you want to start with? Okay. So how many do you have? Okay. So you look on the periodic table for it, right? So 3 times 40. We're just going to keep them simple. Okay. What's the next one? Phosphorus. Okay. So you put these in parentheses. Okay, phosphorus, how many do you have of those? 2. You got to include the ones on the other side. So you look for phosphorus up there, 32, about 32. So essentially you have 2 times 32. Okay, how many oxygens do you have? 8. So that's 8 times 16. And then you have the total. Okay? It's very straightforward. You have your calculator. Everything is fine. It's just a very simple procedure to get that molar mass. Okay? So let's see how they do it here with the next slide. Okay, 1 formula unit there. 3 times calcium, 2 times that, 8 times 16, 318.18 AMU. Okay, and that is the moles, grams per mole as well, okay? So essentially you have that. Now a mass spectrometer is used essentially to determine the mass of the individual atoms, and we talked about that before. Yes?
So formula mass.
Yes, it's just true for ions, for ionic materials, because they don't really have molecules. They more like have a crystal structure that has a combination of both of them, okay? And that would be the true for anything. Like say, for example, silicon dioxide, which is sand. Okay, that's a huge crystal structure also. Okay, so what would be the molar mass of that?
28 plus 32.
Yeah, 28 plus 32 is 60. 28 plus 32 is equal to 60. Okay, grams per mole. And you could go away from ANU and just make it grams per mole there if you want. It's very easy, straightforward to look at, okay? Now, percent composition, this is essentially what you're doing next to find out what is the percent of each of the elements in a substance, okay? And this is something you just have to learn just by practicing it. But let's just look at the previous example we had before. silicon dioxide. Okay, silicon dioxide. Okay, what is silicon there? It's 28, right? 28 plus 32 equals 60. Okay, now the percent composition, what would be the percent composition of silicon? You have the number of moles of that divided by the molar mass of the compound. So what would that be equal to? Well, you take the 28 there, because you have one mole of that, times the molar mass. So you have 28 grams divided by the molar mass of the compound, which is 60, SiO2, and this is Si. Okay? So then you could just do the math and figure out what the percentage is. Okay? If you had your calculator, you could do that. It's very straightforward to do those. Now, what would be the percent of the oxygen in it? Well, that would just be 32 over 60 grams of oxygen over 60 grams of SiO2. That's the percent of the element in the compound. Yes.
Is N in the formula just
The number of moles. Like here we have 32. I already put it in there. 2 times 16.
so N in that equation will be 2?
Yeah, for oxygen, but 1 for silicon. Okay. So essentially you have the things there working together there to get these different things again. So let's look at the next pointer here with this. Okay, now N is the number of moles in the compound here. Okay, so essentially you have these things related to it. C2H6O. Now these percent composition stuff, this will not be on the exam, okay? But the molar masses will, like we did in the calculations, okay? This is why it's a kind of like a fungible thing between them. Okay, so basically, how many carbons are here? Huh? 2. Okay, so first let's get the molar mass. 2 times, oops. 2 times 12 divided by 47 times 100 is that. And you can figure out exactly 46 and you get 52.14. The amount of oxygen is 13.13. How much is the amount of oxygen? If you just want to figure out the percent, well, you can subtract these numbers from 1. 100% minus 52 minus 13, if you want, to get the amount of oxygen in it. Okay, it's kind of like a shortcut if you're asked to figure out all of them together, but the total is always equal to 100, and that's essentially how they did there. That's the N. Okay. Now, percent compositions and empirical formulas, okay? And the key thing is regarding all these things, empirical formulas has to do with a simple topic of the percent composition. The empirical formula is the mass ratio of each element. Okay, and it's a standard one. Like as I said before, sodium chloride, the empirical formula is NaCl. Okay, so the mass ratio of thing, you have a 1-to-1 relationship with that. Okay, how about H2O2? What would that empirical formula be? If you just look at the mass ratio of each of those elements, what is the common factor associated with that? 2. So this is the molecular formula. This is the empirical formula. And I want you to keep it being that simple. Sorry, empirical formula. My spelling got messed up. Okay, C6H12O6. What's the empirical formula of that? Well, this is CH2O. What is the common factor? 6, okay? And that's what one reason sugar, or glucose in this case, is called a carbohydrate, because it appears there's a water molecule there. But the real structure is a little bit more complicated than that, okay? So essentially you have the mass ratio of each element associated with that. And essentially what he's showing you here is how to make these conversions to do this. Determine the empirical formula of a compound that has the following composition by mass: 24.75, 34.77, 40.51%. Okay, now, because this is the way percents are based on, and you got to have some mass associated with it, what's an obvious thing you could use for how many grams of material you're trying to convert? Well, you to start off with 100 grams. Why does that make it easy if you have 100 grams of this? Okay, MNO, and you don't know this is X, this is Y, and this is Z. So essentially why is 100 grams useful? Right, so essentially you have potassium is 24.75 grams of potassium. You will have 34.77 grams of manganese and 40.51 grams of oxygen. Okay, what's the next step? You take the grams of something and convert it to what? Well, let's look. 39.10 grams per mole, right? So you convert it to moles. 24.75 grams of potassium, and then you have the conversion, 39 grams, and I'm just going to keep it simple just by keeping the round it. 39 grams of potassium is 1 mole. Okay, and essentially you can get the number of moles of potassium from that. The grams cancel. How would you do the same thing for manganese? Well, for manganese, you do the same thing. 34.77 grams of manganese, and then you draw the line in. Okay, look for manganese on the periodic table. It's 54.9 grams of manganese. That is moles of manganese. And then you do the same thing for oxygen, 40.51 grams of oxygen. And it's 16 grams of oxygen per 1 mole of oxygen. And essentially you do the math there too, okay? Does everybody understand the logic? Okay, what can you say what you don't understand? Well, you're given that it's percent composition, right? Okay, if you have 100 grams of material and your potassium is 24.75%, and you have 100 grams of material, how many grams of potassium would be there? 24.75. You start off with 100 grams of material. You're given this is 24.75%, right? You change it to a fraction, multiply that times 100. That'll give you that amount of grams of potassium. Okay? It's a direct conversion. It keeps it simple. You could use 60 if you wanted, but what's the point? Because you're given a percent already. Percent is essentially the fraction. It's the fraction times 100 into 100. So it's like 50% relative humidity. What does that mean? Well, you have 50% humidity in the air about what the air can hold at a certain temperature, okay? So essentially, if you know what the percent is, okay? So essentially, it's just a matter of switching from percent to fraction, and then having the 100 grams of material to keep it simple, okay? So now what I'll do is I'll erase the thing and we'll go back to the thing again. And you can see how this works. There you have the number of moles of potassium. That's the first part. The grams of potassium cancel. Then you have the grams of manganese. You have the number of moles of each. Okay, then you have that regarded to that. Now, what do you notice about the potassium and the manganese? What do you notice about the number of moles of each of those? They're almost the same, so you can divide them by each other. You take the one that's the lowest one and divide it into it. So basically, you go through and divide, go through this and divide each of these by 0.6329. 0.6329, because you want to get the mole ratio. And this is by 0.6329. Yes, that's correct. So essentially you'll get a 1 here, a 1 here, and this will be a 4. So you know that it is essentially KMNO4. That's how it works. Okay, and again, the only way to learn this is to practice. But why do we ask you to do this or whatever? Because essentially it's going to be leading to the later stuff that we got in later in chapter 3, where we're talking about the stoichiometry or the ratios between each of these. Okay, so here we have the relationship between both of them is about 1. That's 1, and that's 4. So it's KMNO4. Okay? And again, the best way for you to do it is just use your textbook to work on the problems and then go through each part. Okay, now if you're, there are certain ways to get the molar mass of something that's a solid. And for example, they're burning ethanol in a tube, collecting the water and collecting the carbon dioxide, and seeing how much grams of each of the material are in there, and then determining the number of moles of each. And you can get the empirical formula is that. Then you look for the common factor between all of them together, and you get the molecular formula divided by the smallest subscript, and that gives you the empirical formula of C2H6O, okay? So essentially, that's another example there. Now, a process in which one or more substances is changed into one or more things is called a chemical reaction. So essentially you have like this, A plus B goes to C plus D, okay? Or let's just keep it very simple. Iron plus oxygen goes to iron to oxide, okay? And the law of mass conservation essentially says the amount of the reactants equals the amount of products. So you have the reactants equals the products. All has happened is that the things have rearranged. So you start off with iron. Oxygen is O2 here. This goes to Fe to O3. So in this case, you have CD associated with this. This is CD now, not thing. This is a special kind of reaction, a combination reaction, or AB. AB is simpler. So this is a combination reaction. A plus B goes to AB here, okay? But basically, the key thing is what you're doing with these is essentially you have the amount of materials on one side in grams will give a certain amount of grams of material on the other, okay, depending on what the reaction is. But they all have to balance. It's all dependent on how much iron you have and how much oxygen you have will give you how much product. Now, If you are grilling hot dogs and you have 2 hot dogs and 4 buns, how many hot dogs and buns can you get? If you have 4 hot dogs and 2 buns, how many hot dogs and buns can you get? Only 2. There's an excess of something. So we'll get to that also later in this chapter. But that's called an excess reactant, okay? So it's an unbalanced reaction. But the key thing we have to learn first is how to balance equations. So essentially, a chemical equation uses chemical symbols to essentially show what happens during a chemical reaction, okay? The reactants go to products. The key thing about this is the moles of reactants equals moles of products. Equals, okay? You have moles of reactants equals moles of products. Why? Because in chemical reactions, elements are not created or destroyed. They are what? Rearranged, correct. Okay, so for example, with water, hydrogen plus oxygen goes to form water. That's a combination reaction. Okay. And 2 hydrogen molecules, 1 oxygen molecule, and 2 water molecules. Okay. And it represents this. The plus means reacts with. This means reacts with. Reacts with. This means to form. Okay? Essentially, the hydrogen atoms, what has happened to each of them? What has happened to each of them? Yeah, the hydrogen atoms first. The first step before the bonding to the oxygen. They separate, yes, okay? You have, and the oxygen also separates. And then they reform. Okay? That's called the chemical mechanism. That's the reaction that takes place. So essentially you have the hydrogen like this, and a hydrogen like that, and an oxygen like this. They all break. This breaks that, this breaks that, and then they form new bonds. And I'm making it simple there to show that. Does everybody see how that works? You got to have those one break and then the other ones form to get that, okay? How to read chemical equations? Well, essentially 2 atoms of magnesium plus 1 molecule of oxygen makes 2 formula units of MgO, okay? And this is a salt, so it's atomic formula units in this case. 2 moles of magnesium plus 1 mole of oxygen makes 2 moles of magnesium oxide. 486 grams of magnesium plus 32 grams of that makes 80.6 grams of magnesium oxide. Do the numbers on both sides total. 48.6 plus 32 equals 80.6. Is that true? Is that true? Yes, because the mass is the same on both sides. Okay, so essentially, this has been converted to moles to grams in the case of that. Okay, so essentially you have those things together. It is not 2 grams of magnesium plus 1 gram of oxygen makes 2 grams of that. It's not that simple. Okay, this is a chemical relationship that has to do with the number of moles of them. Okay. Now, balancing the chemical equations. That's the next important part regarding this. And what I'm going to do is essentially introduce the topic. Sorry, we lost you. All right, we gotta fix it again. I gotta share the screen again to you here. Okay, balancing chemical equations. Can everybody hear me there? Can you still hear me?
Yes, we can.
Okay, we lost the internet on this side. Balancing chemical equations. This is the next part essentially you have to do to understand how these things work. Say, for example, if you had 34, oops. If you have 30, if you have 34 grams of aluminum and you burn it in oxygen, how many grams of product will you get? Grams of product, which is aluminum oxide, Al2O3. Okay, so you have 34 grams of aluminum, you burn it in oxygen, how many grams of product will you get in aluminum oxide? Okay, that's the first thing you have to do. So essentially what you start with is you write the chemical correct formula on the left side of what's reacting. So essentially you have aluminum here plus oxygen goes to form aluminum oxide, Al2O3. Now look at that obviously. How many aluminums do you have on the left? 1. How many on the right? 2. So think logically. You go back this way, you check this with that. So now what do you have to do there? Well, you put a 2 in front of that. Balance it, right? Okay, how many oxygens on the left? 2. How many on the right? 3. So essentially you would have to do that, the same thing here, and you put 3 halves there. Okay, because the 2's will cancel. You'll have 3 now on the other side. So essentially it's now sort of balanced, but fractions aren't allowed. So this becomes 4Al plus 3O2 goes to form 2Al2O3. Is it balanced? Yes. We essentially went back and forth across. We went back that way, and then back again to get it balanced. Then you did the multiplication by 2 times the whole thing to get rid of that fraction. You can't have the fraction in there to get both, okay? So essentially we have now balanced it, okay? Now the next few slides are gonna go over the procedure for how you balance equations. So let's erase the slide again. Okay, write the correct formula for the reactants on the left side and the correct formulas for the products on the right side of this. Ethane reacts with oxygen to form carbon dioxide and water. Well, ethane, because you're not organic chemists, is C2H6. Okay, C2H6. How many carbons are there? Huh? 2, right? How many on the right? 1. So what do you have to do to balance it? Put a 2. Okay, how many hydrogens on the right? 2. How many on the left? 6. So what do you have to do there? You put a 3 in front. So now you have 6 on both sides. Okay, now how many oxygens do you have on the right? 3 plus 4 is 7. Okay, so you have to have 7 over here. So you put a 7 halves there. Okay, but you're not allowed to use fractions in them. So you multiply all of it by 2. So this now becomes 4, and this becomes 6. So essentially, I will erase that right now, and then we'll go to the slide. You can follow it easier than my handwriting, okay? So let's go through and balance this equation. And again, This balancing is going from one step to the other. Now, when my sons were little, I think in elementary school and then a little in high school, this is the kind of thing I would give them, little things about balancing. I taught them a little bit of chemistry when they were in junior high and even in elementary school, okay? They could do this stuff too. It's very simple to go back and forth thing till you finally do it. Please do not overcomplicate it and make it harder than it is, okay? So let's see where we go with this. You change the numbers in the front to make the numbers of atoms on the same on both sides. You do not change the subscripts. Why not? What happens if you change the numbers underneath it? Yes, very good. You're making a new compound and you can't do that. Okay? So for example, if you had something like this, hydrogen plus oxygen goes to form water. Okay, but you decide you want to balance it by making H2O2. Is that correct balancing? No, you have hydrogen peroxide instead of water. That's a different compound. So that's a different chemical reaction taking place. So this is not the way to balance it, that with that last one. That's changing the subscripts, and you can't do it that way. Okay, now how would we balance that water thing? How many hydrogens on the left? 2. How many on the right? 2. How many oxygens on the left? 2. How many on the right? 1. So you got to put a 2 in front. Now the hydrogens have changed. How many hydrogens on the right? 4. How many on the left? 2. So put a 2 in front. So essentially you went from one side to the other and back and forth essentially to balance it. It's a very straightforward thing. Okay? The books tend to overcomplicate it. Please don't. Okay? So essentially you can have a bunch of things related to this here regarding these. Don't change the subscripts with this. Yes.
When you put the 2 on the right for the hydrogen, why would you put it just on the oxygen?
Well, because you don't want to break up the molecule. The whole point is you had a water molecule, and putting it in front will break it up, okay? Because there's a bond in between. For example, this is what a water molecule looks like. So you can't put a 2 in front of that. Okay? Balancing chemical equations. You start by balancing those elements that appear in one reactant and one product. So let's do it with this one again, okay? Start with C or H, but not O. Okay? 2 carbons on the left. What did I have you do next? Well, then you go over to the right, like that. 1. Multiply CO2 by 2. That'll get it fixed. So then you put a 2 in front. Okay? You now have that. Now the next thing is what? The hydrogen. Okay? 6 hydrogens on the left, 2 on the right. So multiply it by 3. That answers your question. Okay? You have a 3 here. Now you have 7 hydrogen, 7 oxygens. Balance those elements that appear in 2 or more reactants or products. So now you have 7 oxygens, 2 oxygens on the left, 4 plus 3 is 7. You multiply by 7 halves, both sides. Okay? So you have 7 halves, the oxygen by 7 halves there. To remove the fraction, multiply both sides by 2. That's it, and some more steps. Very straightforward process. You check and make sure you have the same number of each type of atom on both sides of the equation. Now let's look at something more complicated. C11H22O, no, C12H22O11, that's sucrose, plus oxygen goes to CO2 plus water. How hard would that be to balance it? Well, you follow the same process. How many carbons on the left? No, how many carbons on the left? 12. How many on the right? 1. So you put a 12 here. See it? Okay. How many oxygens on the left? No, how many hydrogens on the left? How many on the right? 2. So you put 11 here. Okay? So how many oxygens on the left? 13. How many on the right? You have 11 plus 24. So there are 35 on the right. On the right. Okay? On the left, how many are there? These are 11, correct? You have 35 on the right. So you can provide, you have the 11 there. So you keep the 11 on there also. So how many do you still have to add to it? 12, okay? So essentially you have to add 24. So the 12 goes here for that. You now have this 11 plus 24 equals 35. So it's now balanced. C12H22O11 plus 12H2O, 12 oxygen, sorry, goes to 12 CO2 plus 11 H2O, like that, okay? And again, that seemed to be a complicated problem, but it really isn't. So let me go back to the slide again, show you with the things there. For example, with this, you have the reactants and the products there. So essentially what you're doing is, essentially, this is the next thing we're going to be working on next time is amount of reactants to products going grams to moles using the mole ratio and then moles to grams on the other one. And basically this is the beauty of Hein, because he, in that book, in chapters 7 and 8, spends a lot more time spreading out the problem, so you could work on that. So I'm encouraging you to work on that this week also. Now, the beauty of this stuff is it'll help you to, if you work the problems for this, this will help you with the problems to get ready for the exam on Thursday also. So there's good overlap between what you're doing now and what you have to do now, okay? Now, any questions of those of you who are virtual?